Do you like it more?
Yes.
Good. I won. I win. Or like my daughter says, I win. So can we discuss as a group? No pun intended. Can we discuss as a group? You laughed. I told a Ted Williamson joke and you laughed. Ted Williamson, have you had him? That was a Ted Williamson joke, right? Alright, can we discuss back as a group? What did you find in this first problem? When you took the order of 4 and the order of 3 and compared it to the order of 4, 3, what did you find?
They were different dividers.
Any connection between them? Right, so each of these orders seem to divide this order. What about this second one? And were there any other conjectures you could make? Just look at this one example. What was the order of 4 and the order of 3? Is there anything more you could kind of derive from this one first example? And the question is, did whatever you derived for this first example, did it extend to the second one?
Yeah.
Yeah? So what was the conjecture that you came up with that seemed to work? That's right. You can, as you were actually calculating, I saw some of your desks, you're actually calculating one by one. You know, sometimes you hear, well, people shouldn't calculate too much because they're losing the concept. But sometimes you can conceptualize as you're calculating. So you can actually see, well, when am I going to get 0, 0? I'd have to keep adding till they're both simultaneously going to be 0 at the same time. So you can see that. And so I thought that was really interesting looking around at your desk and actually seeing the computation. So, so that's the conjecture I think that we're coming up with. So the conjecture is that you're guessing that the relationship between these two are going to be the LCM of the order of A and the order of B is going to be the order of the the order of the element and when you correct in the direct product group. So that's the solution of for the conjecture. So if we have G1 and G2 are finite are groups with G and G1 and H and G2 both of finite order, then the order of an element, an arbitrary element, is going to be the LCM, least common multiple, of the order of G and the order of H. It's cool. I really like number theory. So how do we prove that? Well, kind of like you were at your desk. When you compute like that, you get a feeling for how that works. So the first step is to identify the identities in G1 and G2, and you don't want to call them both E, because if you call them both E, then, like myself today, a 15 became a 5. So you start to get messed up with which E is which E. What I want to show is two things. First, I want to show that if I take this element GH and I raise it to the LCM, that I get back to the identity. That will tell me that it has the potential for being the order. The second thing I have to prove is that it actually is the first time it happened. So if I set M to be the order of G and N to be the order of H, then the LCM of Mn is the smallest integer such that that's a definition of LCM, such that both M and N both divide it. And therefore, the LCM can be represented as M times R has to be, for some R has to be the LCM, and N times S has to be the some kind of divisor. And that's just the definition of dividing. So from that, I can get that if I take GH and raise it to the LCM, well, what's the definition of raising to the LCM? You're doing it separately for each one. So this is just the definition of what we mean by Cartesian, the direct product. And then, well, that means that we have this, but because this is the order of G and this is the order of H, and multiples of orders turn it back to E as well, we get the identity back here. So that's by definition of order. Or it's actually a corollary to the once you have the definition of order, it's falls out from that any multiple of the order is also going to bring you back to the identity. And we've seen that too when we've computed in class. So what we can conclude is that the order of GH is less than or equal to and divides the LCM of M and N. Now I have to show the other way, that LCM divides the order of G and H. So step 2 is to show that this is actually the smallest of such powers. So assume there's a k that takes me back to the identity for some k. Then I know that, by definition, this is what I mean by that. And that means that g to the k is e in G1 and h to the k is e in G2. That means m and n divide k. Well, then the LCM also, if you have m and n both divide a k, then the LCM also has to divide the order of m and n, and therefore it divides in the other direction, and you have equality. So it's a typical proof of equality showing it divides in one direction and it divides in the other. So by the way, I'm going to skip this, but I think Fraley talks about this, that anything that we do for the direct product of two groups, so far anything I've done extends to n groups. So in that case, if I had the orders of elements of each one of these groups, then the product of the orders would equal the order of the full thing. If I have the order of an element in the direct product, then I can use the LCM of all of those to become the order of, so all of this extends. So I wanted to give you the definition of normal subgroups. You kind of can't see why normal subgroups are so cool until you get into homomorphisms and see the original group collapsing into a smaller, more manageable group. But and it was my desire actually to get to homomorphisms in this section right now in this week, but it doesn't look like I'm going to get to it in this week. So I'm going to reserve it for the week after spring break. What is a normal subgroup? H is a normal subgroup if for each G in the big group and each H in the subgroup, G, H, G inverse belongs to H. Why are normal subgroups so important? Well, because we can define a multiplication on the cosets. You kind of get an idea of why they are going to be important in terms of homomorphisms. Because it turns out that I can define for normal groups only an A1H coset A1H star coset A2H is equal to A1 star A2H. And if you had Fraley before, you recall him doing a pretty decent job of looking at normal groups, normal subgroups. So if H and K are normal subgroups of a group, we can define what we mean by the product of these two H and Ks by defining it to be H times K for K and the little k and big K, and little h and big H. And it turns out for normal groups that this H star K is a subgroup of G. For the group in this class that's doing, for the subgroup in this class that's doing the advanced problems, try to see why it's not true when H and K are not normal. See if you can explain why I need that condition of normality. So I'm not quite sure I remember exactly how Fraley introduces this, but the definition is in the Fraley book. And once he introduces this, the way he shows you the importance of normal groups is by looking at factor groups. That's where they become important. You can't talk about factor groups without looking at normal groups first.
Is there a notation for a normal subgroup? Is it like a sideways triangle thing?
I don't think Fraley uses that notation. No, I didn't see that he did. There probably is. In fact, most books use capital N for the normal subgroup, but I needed two, so I used my H and K's. That resulting subgroup is called the internal product of H and K. So I wanted to give you an example, and I wanted to use the group of units mod n, which I don't think that Fraley brings early into the book. Gallian does, though. He uses the group of units right away. And I saw some of you were using the group of units inside for some of your examples. So for example, if I have U of 14, it's what the group of units is. It's all the elements in Z14 that are relatively prime to 14, and the binary operation on this group is multiplication. The identity would be 1. Sound familiar? Vaguely? You had Fraley, right?
I don't think that, no, we didn't have Fraley.
You used Gabe.
I had Dr. Z.
What did you use?
I don't remember. I think I have a PDF.
He's a Gallian. I think him and I used Gallian one semester when we taught it together. So these elements have a multiplicative inverse and form a group. If you haven't seen this, try to show what the multiplicative inverses are. They're not going to be reciprocals because there's no fractions in here. So for example, you'd want to multiply something by 3 to get 1. Because you're modding by 14, you have to figure, you can actually make a little table in Excel and actually see what one of these elements you'd have to multiply 3 by to get 1. So each one of these elements in here has a multiplicative inverse. So if you haven't done that, that's a really good in-class assignment type work that you can do and get your hands on and get a feeling for what this group has. It was Gallian? Yeah, him and I taught it together a while back and we used Gallian. I like Gallians. Gallian is good. So for homework, which I will quiz on after the spring break. I'm around during spring break, so it's not like I'm gone, so you can ask questions. Consider that U28. In class, I wanted you to develop the Cayley table for U28. Don't feel like that's an onerous task because right now in class you can make that table, make sure you have it right. It's not that bad because you're only looking at those elements that are relatively prime to 28. And you're multiplying. It's not like you're doing something with quaternions. So the homework problem is to let H be the cyclic group formed by 9 and K be the cyclic group formed by 13. These two subgroups are going to, are multiplication, the binary operation is multiplication, and you're housed within U28. Find what the intersection is going to be, and find the elements of the internal product. I was tempted to do this problem for you so you could see it, but I want you to, I don't think this is hard. So go back to the definition of internal product and actually calculate out the what H star times K is going to be, and then make the Cayley table for H times K. And I promise you it's not bad, it's all multiplication, so it's not going to feel bad as you're doing it, like the quaternion group.
So just to clarify, if you're taking the direct product of two subgroups of a given group as the internal product, whereas the direct product of two groups in general is the external?
Well, no, the direct product here is going to be, yes, you can think of it that way, right. The internal product won't be well defined if you don't have normality. Right,
Normal subgroups
right,
of a given group, whereas
right.
the external product is just
Any groups.
Okay.
You can patch together any groups. So you can put, you know, D3 together with the quaternions. I don't know why you'd want to do that, but you could do that.
So
Now you know I don't hate you because I could ask you for the Cayley table for that one.
So you can call any subgroup a direct product, but specifically if it's a normal, it's called an internal.
No, I don't. It's not going to work out if you have. You won't get that it's a subgroup if you don't have normality. You need that normality condition. Okay, so I was asked to actually figure out which slide this appeared on, so maybe I'll write it down now. That was slide 44. So this is an internal product theorem, and I don't want to prove it in class, but if you want to, and I think this might be something new to look at internal products. So if you're in the advanced track, you might want to prove this one, and it's not scrambled. So there's a lot of nice properties. I'm skipping. Actually, Fraley has listed a nice number of properties in section 11 on external products. I don't think he talks about internal products, but each one of these two types of products have nice properties that follow. So this is for everybody. If you have a finite group with identity E, and if H and K are normal subgroups of G, with the intersection of H and K equals empty set, which you know something about now because you fooled around with those during the past week, then the order of K times the order of H is going to equal the order of G. And if I have this, is it true that G is equal to H times K? That the entire G can be expressed this way? So you're going to have to play around with some examples of groups. I thought it was great that I was looking at certain examples where I was trying to find an intersection that was not just the identity. And of course I went to my symmetric groups because that's the nicest. If you want to find a counterexample, go to symmetric groups. Someone in the class said, oh, you just made me do the quaternions. I found a counterexample there. So you can take any one of the examples that we've been building up and start using them to test out the first part, whether the entire group can be written in this way if these conditions are met. If you think it's true, prove it. If you think it's false, you're going to think it's false for a reason. So I'd hope you have a counterexample. So this was on slide 47. And I leave you with that. I was in homework mode. Does that give you time to enjoy your spring break? But I mean, I think this is enjoyable, but I didn't realize how nasty the quaternion group Cayley table was going to be, so I do apologize for it, but I did it myself. It's annoying.